Okay, so good evening, all of you. Welcome to this fourth lecture of refrigeration and air conditioning. Uh, so, my request to all of you, please join when the lecture should actually start. Like this lecture was expected to start at 4 p.m. So, you should have joined before it. Okay, so what happens? These 10 minutes are now wasted. So, it may happen that I will extend this lecture and 10 minutes by 10 minutes. Okay, it may happen in future, so don't do this. Try to be very punctual. Okay, so weather outside is very good in Pandharpur. uh, uh, so this just wait a minute, I'll set up for the lecture. Okay, so we'll start. So those who are in Pandharpur, they must be enjoying that the weather is very good in Pandharpur now. It is raining outside. Okay, so I'll just take a review of our last three lectures. So we started with the introduction to the subject, refrigeration and air conditioning. So we have seen the examples of this subject. Then we started with the Carnot cycle and reverse Carnot cycle. So why we have started with these cycles? Because these cycles are expected to give you maximum efficiency or maximum coefficient of performance. So last lecture we have solved the problems also related to reverse Carnot cycle. So if a refrigerator that works on a reverse Carnot cycle, we generally call it as a Carnot refrigerator. So we have solved the problems. I think our last example was related to ice factories where we have to produce ice. So there we have to calculate how much power input we have to give to the factory, and we had calculated. Okay, so up to now we have covered these things, and also we have seen the some units. So unit of refrigeration is ton of refrigeration. So 1 ton is equal to 3.5 kilowatt. And how we calculated that derivation also I have showed you. So 1 ton of refrigeration is the heat required to convert 1 ton of ice into water at 0 degrees Celsius in 24 hours. Okay, or we can take the reverse also. We have to freeze 1 ton of water into ice at 0 degrees Celsius in 24 hours. So both way we can go. We can go for melting, we can go for freezing. In both case, same energy will be required. So that energy, what we call it as latent heat. So when we are changing phase from liquid to solid or solid to liquid, that time temperature remains same, but uh, latent heat is added or it is removed. So that was our last example, and today we'll move towards Bell-Coleman cycle. Okay, so this is our chapter. So up to now we have seen the reverse Carnot cycle, and we have so reverse Carnot cycle contains all the processes as reversible. So if the process is reversible, all the processes in reverse Carnot cycle are reversible. But a reversible process in actual world it is not possible. Okay, so in actual world there are various irreversibilities. For example, friction, which causes a irreversible process. So there is no process in the universe which is a reversible process practically. Uh, so again, the reverse Carnot cycle contains two isothermal processes and two isentropic processes. So isothermal processes, naturally they are very slow, and isentropic processes, naturally they are very fast. So a cycle cannot contain one process which is very slow, then next process is very fast. So that again it is practically impossible. So we have to go again slow to fast in that manner. So because of limitations of reverse Carnot cycle, we are not using it, but definitely we have some modifications. So Bell-Coleman cycle is one of it. So what is the Bell-Coleman cycle actually? So I will read this. So this cycle may be thought of as a modification of reverse Carnot cycle as the two isothermal processes. So reverse Carnot cycle contains two isothermal processes and two isentropic processes. So these two isothermal processes of Carnot cycle are replaced by two isobaric heat transfer processes. So isobaric means the pressure remains constant pressure processes. Okay, so in reverse Carnot cycle we had two isothermal processes. So heat is added at constant temperature, heat is released at a constant temperature, but we are replacing those constant temperature processes by constant pressure processes. Okay, so heat will be added at constant pressure and heat will be released at constant pressure. So what cycle we get? That cycle we call it as Bell-Coleman cycle. It is also known as reverse Breton or Joule cycle. Okay, please write it down. So those who have joined now, so they have to write this, whatever on the screen. So I hope all are having their notebook and pen with them. So because today we are going to take one day revision. For that pen and that notebook and pen will be required. Okay. So don't just sit idly. Please involve yourself. Okay, so this Bell-Coleman cycle, it is also known as, so AKA stands for also known as, it is a slang, so it is also known as the reverse Breton or Joule cycle. So what is it? We'll see. So what you see on the screen, so there are two heat exchangers, and one we have a turbine, and it is generally called as expander, and another we have a compressor. Again, at the top we have a hot reservoir. So in general, what we call it as source. Okay, and here we have cold reservoir that we in general call it as sink, right? So see here, the process of refrigerator is same here. It takes heat from the cold reservoir and it transfers that heat to the hot reservoir. Okay, but two additional processes are here. One is turbine, so that is the expansion process, and another is compressor, that is again a compression process. So in this case, we'll see how the processes are. So if you are not drawn the diagram, you can draw it. So this is a general representation of Bell-Coleman cycle. We have two heat exchangers. It is taken from the cold reservoir. It is transferred to hot reservoir. In between, we have one expander, that is a turbine, which is coupled to compressor, which is whose function is to compress the air. So up to now, we have taken air as a refrigerant. So air is a heat carrying medium, which will transfer heat from low reservoir to hot reservoir. So we are not gone into the commercial refrigerants yet, R12, R22. Up to this point, air is our refrigerant. Air will carry the heat from low reservoir to hot reservoir. Okay, so I hope you have drawn the diagram. Now we'll see the processes. What is the difference between the reverse Carnot and Bell-Coleman cycle? So this figure is very now familiar to you. We have seen this in last two lectures. First, we have seen the Carnot cycle, and as all processes in Carnot cycle are reversible, so we can reverse their direction, and what we get is reverse Carnot cycle. So what you see here, first is a PV diagram, in that these four are reversible processes. Okay. So here 4 to 1 is constant temperature, heat addition, heat rejection. Then 1 to 2 is expansion, 2 to 3 is constant temperature, heat addition, and 3 to 4 is compression. Okay. Now what I will do, I will replace this constant temperature processes. Here in this case it is 4 to 1 and 2 to 3. I will replace this constant temperature processes by constant pressure processes. Okay. So what we get is Bell-Coleman cycle. So see here. So in this case, this 1 to 4, this 1 to 4 process is now constant pressure process. Okay. So the pressure remains constant during heat rejection. Now heat is rejected here, and again 2 to 3. So here 2 to 3, it was a constant temperature process, which is now a constant pressure process. So 4 to 1 is a constant pressure heat addition. So heat is added at constant pressure. Then we have 1 to 2, that is isentropic compression, and 3 to 4 is your isentropic expansion. Okay. So this is a pressure volume diagram. Similarly, we have a temperature entropy diagram. Here what we have done, we have replaced this 2 to 3 and 4 to 1 by constant pressure processes. So that is represented here. Okay. So 4 to 1 is no longer, so this was previously constant temperature process. Now this is a constant pressure process. So again 3 to 2 is also constant pressure process. 1 to 2 and 3 to 4 are isentropic processes. So the entropy, so in this case entropy will remain constant. Okay. Now a question may arise from diagram, how we can identify which one is an expansion process and which one is a compression process. Okay. So this is a very general query. So see, in compression what happens, we are increasing the pressure. So if I take this diagram, okay, in this diagram I have to see where pressure is increasing. So obviously pressure at point 1 and pressure at point 2, they are different. So pressure at point 2 is greater than pressure at point 1. So that is a compression process. So we are increasing the pressure. Again, see here, pressure at point 4 is less than pressure at point 3. So pressure is reducing from 3 to 4. So that is a expansion process. So when the pressure is reducing, that is the expansion process. For example, turbines. When the pressure is increasing, that is a compression process. What we, for example, compressor, right? So draw this two diagram, PV and TS diagram. Okay, so this is what we call it as Bell-Coleman cycle. Okay, so what is a Bell-Coleman cycle? We'll see what are the processes. So 1 to 2 is isentropic compression. So see in the diagram, 1 to 2 is isentropic compression. Isentropic means the entropy remains constant. So if you see the TS diagram, here you can see that 1 to 2, in that case the entropy remains constant. So if I take this is as S1, S1 is equal to now S2. Entropy at point 1 is equal to entropy at point 2. So that is why it is a isentropic process. So what is happening here? The air drawn from the refrigerator to the air compressor cylinder, where it is compressed isentropically. Okay, so air is drawn from the refrigerator to the air compressor cylinder, where it is compressed isentropically. So this area, in this area, so this area is the area of refrigerator. So in this area only refrigerator will work. This area is related to compressor. Okay, this area is related to again condenser mostly. So this is related to condenser, and this is a expanders. Okay, so expander example we can take as turbine, or we can take a pressure relief valve. Okay, so various instruments are there to reduce the pressure. Okay, now next process is constant pressure cooling process. So that is a 2 to 3. So what happens in compression? So in general, when you compress the air, its temperature increases. Why it increases? Because its pressure increases, right? So as the pressure increases, the temperature of the air is also increasing. So at the exit of compressor, here at point 2, we have very hot, high temperature and high pressure air. We are passing it through the condenser. So that is the constant pressure cooling process. The warm and compressed air is then passed through cooler, where it is cooled down at constant pressure. Okay. So compressed air is passed to the cooler, where it is cooled down at constant pressure. So what is saying that condenser is operating at constant pressure. Its function is to cool the air, to reduce the temperature. Okay. So you can see from the TS diagram here. So you can see 2 to 3. So temperature at point 2 is T2. Temperature at point 3 is T3. So there is a difference between T2 and T3. So what is happening in 2 to 3? It is actually cooling the air. Okay. So that is a constant pressure cooling process. Though it is said that this condenser is operating at constant pressure, it is not a actual case. So actual मध्ये काय होत असतं, नेहमी त्यामध्ये pressure drop होत असतो, right? So the thing is, whenever air passes through a variable cross section area, right? So that time the pressure changes. So generally what happens if you pass air through a filter, एका फिल्टर मधून तुम्ही एअर पास करा, त्यामध्ये काय होत असते, प्रेशर ड्रॉप होत असते. ज्यावेळेस तुम्ही काय हीट एक्सचेंजर वरून एअर पास करत असता, तर त्यामध्ये काय असते, बरेचसे छोटे छोटे चॅनल्स असतात. ठीक आहे. तर तुम्ही गाडीचा रेडिएटर काढून बघितला, त्यामध्ये काय असते, कॉइल्स असतात आणि कॉइल्सवर प्लेट्स असतात. ठीक आहे. तर प्लेट्स कशासाठी असतात, तर त्यामुळे एरिया वाढतो आणि हीट ट्रान्सफर रेट वाढतो. पण त्यामुळे काय होतं, ज्यावेळेस एअर त्यातून पास होते त्यावेळेस काय होतं, त्यामध्ये pressure drop होतो. ठीक आहे. So in actual the pressure reduces, but in Bell-Coleman cycle what happens, air is cooled at constant pressure. So that heat transferred to the atmosphere, that is Q2 to 3 is equal to Cp into delta T. So delta T is T2 minus T3. So this much amount of heat is liberated to atmosphere. Generally we refer it as QH, heat transferred to atmosphere or hot reservoir. Now the third process in this diagram is isentropic expansion. Again, isentropic means the entropy remains constant. So see here 3 to 4 process. Okay. So entropy at point 3 is equal to entropy at point 4. But what is happening in this case? Expansion is taking place. So previously I told you compression means what? Pressure increases. Expansion means what? Pressure reduces. So see here in PV diagram. So what here is happening? Pressure at point 3 is reducing to the pressure at point 4. Now pressure P1 is equal to pressure P4 and pressure at point 2 is equal to pressure at point 3. So we can say P1 is equal to P4. Okay, so here we can say P1 is equal to P4. And we can say P2 is equal to P3. Okay, so what is happening in isentropic expansion? The cooled air is expanded isentropically. That is isentropic expansion. Next is 4 to 1. So 4 to 1, see in the figure, constant pressure expansion. So it is actually heating process, but it is said that constant pressure expansion. So that is not possible. So pardon me. So this should be like a heat addition process. This you can take at heat addition or heat absorption you can take. Okay, so what is happening in this case? 4 to 1. So see in the PV diagram, 4 pressure at point 4 is equal to pressure at point 1 at constant pressure. Okay, at constant pressure what is happening? Heat is being taken from the space. ठीक आहे, जर मला रूम थंड करायची असेल तर मी काय करणार आहे, या साइडला माझी रूम असणार आहे. And what I am doing that I am extracting this heat from the room at constant pressure. Okay, so that is a constant pressure heat addition or extraction from the space. So heat is transfer or heat transfer from the refrigerator to air. Okay, so we have a refrigerator here. Heat is transferred from refrigerator to air. Air will take that heat here. Then what will happen? 1 to 2 isentropic compression will take place. Then that air will be cooled from 2 to 3 at constant pressure. Then again 3 to 4 isentropically that air will be expanded, that pressure will be reduced. Again 4 to 1 it will take heat from the refrigerator. So this cycle will continue. In this cycle what we call it as Bell-Coleman cycle. So 4 to 1 whatever heat being absorbed, it is Q 4 to 1 is equal to Cp. So Cp, as we know, this is a specific heat at constant pressure. So we have Cp and another we have Cv. Cv is nothing but specific heat at constant volume. So this Q 4 to 1 is equal to Cp into delta T. So what delta T they have taken? T1 minus T4. So T1 minus T4, that is nothing but your into Cp, that is nothing but your heat absorbed Q 4 to 1. So this generally we call it as refrigeration effect. Okay, so this is the effect what we are expecting. So that is a refrigeration effect. Or also we give the symbol this as a QL. So here we give it as a QH, here we give it as a QL. Okay. So I hope you all are writing this because this is very important cycle. There will be a derivation on this cycle. Again, examples will be there. Okay, so first we'll solve the derivation. We'll get to know how this formula are being derived. Then we can solve the examples. So can anybody tell me what will be the COP? So if I construct a refrigerator working on a Bell-Coleman cycle, right? So what will be its COP? So yes, anyone from you? So my question I will repeat again. So we have just seen the Bell-Coleman cycle, and I explained all the processes. Now how to calculate its COP? So I want some responses from your side. So Akshay Takle, are you there? Akshay Takle.
Yes, sir.
Akshay Takle. So have you understood the cycle, Bell-Coleman cycle?
Yes, sir.
Then can you guess what will the COP in this case? Coefficient of performance. So you tell me what is the formula for COP of a refrigerator?
No idea.
You tell general formula for COP of refrigerator. What is that general formula we are using for COP of a refrigerator? Any idea?
Refrigerator, huh?
So we have seen in last 2 lectures. So I will show you. So I'll move to the. I hope you have written this diagram. I will draw this again.
Okay.
Okay, so you can mute yourself. So first I will draw the PV diagram. So pressure versus volume. Here we have two constant pressure processes. This is also constant pressure process. Okay. This is a constant pressure process. So these two are constant pressure processes. Others are isentropic processes, right? So I'll just look at it again. 1, 2. Okay. So this is 1, this is 2, this is 3, this is 4. 1 to 2 is a compression process, isentropic compression. 2 to 3 is constant pressure, heat rejection. So heat is rejected into the environment. 3 to 4 is a isentropic expansion. Okay. 4 to 1 is a constant pressure, heat absorption. So QL amount of heat is been extracted from the refrigerator, right? So this is a constant pressure process. Next, I will draw the TS diagram. Okay. So T3 is greater than T1. Okay. So this is a temperature versus entropy diagram. So we have 1, 2, 3, 4. Process 1 to 2 is isentropic compression. 2 to 3 is constant pressure, heat rejection. 3 to 4 is isentropic expansion. And to 4 to 1 is again constant pressure, heat absorption process. Okay. Now what I asked Akshay is what will the COP? So COP of a refrigerator that we know. So always remember when we are calculating efficiency or COP, at the numerator we have to take the our objective. So आपला objective refrigerator मध्ये काय असते तर extract the heat from the refrigerator. म्हणजे काय? So we have to take the QL. So QL is our objective. Then in the denominator we have to take the how much work is required. तर हे करण्यासाठी तुम्हाला किती work लागलं. So we can take this as a W. This also we can write it as QL. So W is nothing but QH minus QL. So this heat rejected to the atmosphere minus heat extracted from the refrigerator. Okay. Now, in this case, that QL, that in last slide we have seen, QL is equal to Cp into delta T. So delta T means T1 minus T4. Okay. And QH we have seen is equal to Cp is equal to delta T. So QH will be T2 minus T3. Okay. Now I will put this in the formula COP. So let us say this is a 1. Okay. And I will put all these values in the formula. So what I will get is Cp T1 minus T4 divided by Cp T2 minus T3. Okay. Minus again Cp T1 minus T4. Now I can take all the Cp's common. Okay. So taking specific heat at constant pressure, that is Cp common out. So if I take common Cp from denominator, from numerator, that Cp will cancel. Okay. So what I will get is COP refrigerator. So if I take a Cp common, what will happen? So numerator will remain same. In denominator, I will get Cp in bracket. So I will take this as common. So this will be T2 minus T3 minus T1 minus T4. Okay. So I have taken Cp common. Now this Cp and Cp will cancel. So what I will get finally is T1 minus T4 divided by T2 minus T3. Okay, minus T1 minus T4. COP of this refrigerator. This we can take it as equation 2. Okay. So write it down. This is just a start of the derivation. We have long way to go. So if you have any problem up to this step, you can ask. Because things are going to be a little bit difficult from this step onwards. So have you written? Anybody? So if you have written, I hope you all are following with me and are writing also, right? So no doubt that on YouTube you can search for refrigeration and air condition related lectures or videos, NPTEL videos, all that you can check. But those sessions are not interactive. Okay, so what advantage of attending these lectures is these lectures are attentive. If anybody doesn't understand any step, so you can directly ask me, right? So I will move to the next step. Okay, now the slide is full. I'll write it here again. COP is equal to what we have just derived, T1 minus T4. This divided by T2 minus T3 minus T1 minus T4. Now what I will do, I will take T4 common from the denominator and I will take T3 from the denominator, this bracket. Okay, so I will do just a little rearrangement. Let's see carefully. So what I will do, I will take T4 common from this bracket. So what I will get is T1. Okay. Now if I am taking it as common, there should be a T4. So when that T4 will again multiply inside the bracket, this T4 will be cancelled. Okay. Minus 1. Okay. So you can cross check again. If I multiply again this T4 into the bracket, T4 will cancel. I will get T1, and this T4 into 1, that will be T4. So again I will get T1 minus T4. Similarly, I will do in the denominator also. So please watch carefully. So I will take here T3 common. So what I will get in bracket is T2 by T3 minus 1, right? Minus here again I will take T4 as common, and this will be again T1 by T4 minus 1. Okay. Now I will take advantage of the isentropic processes. Okay. So for isentropic processes, which follow. So wait, I'll just write again. So we can take this as a case 1 from this case onwards. So we can take this as a case 1. So case 1 will be what? Case 1 is compression and expansion both follow. So they follow the same law, that is PV raised to, here in the power it will be gamma equal to constant. Now in case of isentropic processes, we have an advantage. So I can write this as T2 by T1 is equal to, I can write P2 by P1 bracket raised to gamma minus 1 upon gamma. Again, I can write for T3 by T4 is equal to P3 by P4 raised to gamma minus 1 upon gamma. So this is the advantage we have when we are undergoing the isentropic processes. Okay, so what I will do, I will replace this expression for T2 by T1. So wait. So we are not there yet. So see here, so we have written these two expressions, right? Now see here, from the diagram we can say P2 is equal to P3. How? I'll show you. So we have this Bell-Coleman cycle here. In this we can see the pressure at point 2 is equal to pressure at point 3, because this is a constant pressure process. So that pressure will remain constant. Similarly, pressure at point 1 is equal to pressure at point 4. So pressure at so P1 is equal to P4, because that is a constant pressure process. So P2 is equal to P3 and P1 is equal to P4. Okay, and P1 is equal to P4. So see here, P2 is equal to P3, right? And again P1 is equal to P4. So what happens? These two expressions are same. So these two expressions are same expressions. So I will write this as expression 3. I will write this expression as expression 4. So from 3 and 4, we can say that T2 by T1 is equal to T3 by T4. While I will rearrange this, I will take this T3 here and T1 there. So this will be like T2 by T3 is equal to T1 by T4. So these are what I got here, will be fifth. Now what I will do, I will replace. So replacing T1 by T4 by T2 by T3 in this expression. So let us this expression be some 3 again. So this should be 4, this should be 5, this should be 4, 5, this should be 6. So in 3. So what I will get? I will get COP is equal to T4 into in bracket T2 by T3 minus 1. Again in denominator T3 into in bracket T2 by T3 minus 1 minus T4. I will replace the T1 by T4 by T2 by T3 minus 1. Okay. Now see closely. So there is a repeating term. So if you see this bracket, in bracket T2 by T3 minus 1, this term is repeating. So it is repeated at numerator, it's repeated at denominator. We can take this term common and we can cancel it out. Okay. Taking T2 by T3 minus 1 common out and cancelling. So we are going to cancel it. I hope you all are understanding what we are doing in this step. So let us say this is a step number 7. In step number 7, what we are doing, we are taking this in bracket T2 by T3 minus 1 as a common. Okay, so when I take it as a common outside, these two terms at numerator and denominator, they will cancel out, and what we get here is COP refrigerator is equal to T4 divided by T3 minus T4. Let us say expression number 8. Okay. So this is the expression we have got. Please write it down. Okay, so I will before you writing, I will just explain what we have done up to this point. So we had two diagrams here, PV and TS diagram. We have drawn the Bell-Coleman cycle there. Then we have taken the general formula for COP of a refrigerator. So this is the general formula for COP of a refrigerator. That is a QL divided by QH minus QL. Okay, QL is heat extracted from the reservoir or the refrigerator, and QH is heat released to the environment. So we have just put the values of QL and QH. QL is equal to Cp into T1 by T4. Okay, so this QL, we have taken the formula. QH is Cp into T2 by T2 minus T3. We have put these values in this expression, and we have further solved it. So we have taken the Cp as common. Then we have got the expression number 2. Okay. Then next, what I have done, I have taken the T4 common here. So we have got expression number 3. We have taken T4 common here. We have taken T3 common here and T4 here common again. So first case, what we have, all the compression processes, all the expansion processes, they both follow the same law, that is a PV raised to gamma is equal to constant. Okay. So gamma, what is the gamma? Okay, so gamma is a constant. I will explain. The gamma is equal to, it is a ratio of Cp by Cv. So it is a ratio of specific heats, constant specific heat at constant pressure divided by specific heat at constant volume. So gamma is the ratio of Cp by Cv. Also, we can write it as Cp minus Cv is its gas constant. Okay, so we know the gas constant, that is capital R, from the ideal gas equation. So Cp minus Cv is equal to R, and I will replace this Cp by, from this expression we can write this as gamma into Cv minus Cv is equal to R, or I can say Cv into gamma minus 1 is equal to R. Okay, so gamma is nothing but a ratio of Cp by Cv. So we have taken the expression number 5. How we have taken? Because we have taken the advantage of isentropic processes. So T2 by T1 is equal to P2 by P1 raised to gamma minus 1 upon gamma, and T3 by T4 is equal to P3 by P4 raised to gamma minus 1 upon gamma. Okay. But we have seen from the diagram that the pressure at point 2 is equal to pressure at point 3. So P2 is equal to P3 and P1 is equal to P4. So that's what I have written here. So we can see from this expression that expression number 4 and 5 is nothing but same. So if they are same, so I have written these two expressions. So T2 by T1 is equal to T3 by T4. Okay. So I rearrange the terms. Then I have replaced this T1 by T4 by T2 by T3 in this expression number 3. Then what we get is COP is equal to this expression number 7. Then what I have done, I have taken the in bracket T2 by T3 minus 1 as out as common. Then I have cancelled it. Okay. So taking T2 by T3 minus 1 common out and cancelling, what we get, COP is equal to T4 by T3 minus T4. Okay. So this is the case 1. Few more steps are remaining in case 1. We'll take that and we'll stop today. Okay. So please write this down. Two more steps are there remaining. Once you have written it, please give me a signal so that I can continue. Okay, so Srisagar is saying continue. Okay, I will continue. Maheshinte, if any problem is there, so you can leave. So good that you have taken the permission. Okay, we'll move to the next point. So wait, I'll just add one slide here. Okay, so in previous slide, what we have got is COP is equal to T4 divided by T3 minus T4. Okay. So I will divide the numerator and denominator by T4. Dividing numerator and denominator by T4. So what I get is COP R is equal to 1. So if I divide T4 by T4, I will get 1. Then T3 minus T4 minus 1. Okay. Now, see in the last slide, we have derived here in expression number 5 that T3 by T4 is equal to P3 by P4 raised to gamma minus 1 upon gamma. Okay. So I'll just put it here. So it will be like 1 divided by wait, P3 by P4 raised to gamma minus 1 upon gamma minus 1. Now, what is this P3 by P4? P3 by P4, or we take P2 by P1, is nothing but a pressure ratio. So what we term it as a RP. Okay. So see in this diagram, 1 to 2, what we are doing, we are compressing the air. So P2 by P1, that will give you the compression ratio. Now 3 to 4, what we are doing, we are expanding the air. So like P3 by P4, what will give you is a expansion ratio. So case 1, we have assumed that both following the same law. So compression expansion both follow the PV raised to gamma. So for this case only, we can write P3 by P4 is equal to P2 by P1 is equal to pressure ratio. That is nothing but what sign we are given is RP. So I will get COP of refrigerator is equal to 1 divided by RP. Okay, this raised to gamma minus 1 upon gamma whole minus 1. So this is the expression when compression and expansion both follow the same law, that is PV raised to gamma. Okay, I'll just give the numbers here. So this I can write 9. This I can write it as a 10. Okay, so in problem, if they have given this PV raised to gamma equal to constant, okay, and the gamma for air is the standard value for air, it is 1.4. So when they have given PV raised to 1.4 equal to C, then and then only you can use this formula. Okay, PV raised to 1.4 equal to C. If they are given that both compression and expansion follows this law, then you can use this formula. That is expression number 10. COP is equal to 1 divided by pressure ratio raised to gamma minus 1 upon gamma minus 1. Okay. So there are two cases remaining. So second case is compression and expansion. They both follow this law, PV raised to n equal to C. Now in this case, it is not gamma, it is n. Okay, so that is our second case. And third case is compression follows another law, let us say PV raised to constant, and expansion follows different laws, let us say PV raised to m equal to C. So they both follow the different laws, and then we have to calculate the COP. So we have three cases. Compression expansion follows the same law, PV raised to gamma equal to constant. Second case, we have PV raised to n equal to C. N means obviously n is not equal to gamma, that value may be different. And third is PV raised to n. So compression follows different law, PV raised to n equal to C, and expansion follows different law, that is PV raised to m equal to C. So these two cases we'll take in next lecture. Okay, so I hope you have understood the process up to expression number 10. If you have any problem, you can ask. And next lecture we'll take the remaining derivations. Right? So any questions? So I have not told yet to give the attendance. So I will take the attendance, no issues. But if you have any problem, you can ask. Okay. So I'll ask randomly. So who's here? Pradyumna Vakmode, are you there? Pradyumna? Pradyumna. Hello. Hello, Pradyumna Vakmode. Okay. So where's Sansare? Sanket Sansare. So please reply, otherwise I have to mark that as absentee, even though you are present here. So what I'm asking is, have you understood all the steps? Should I explain again? Huh? Hello. So I think he's having some voice issue. Okay. Anyway, I will stop here today. Apart from subject, if you have any problems, you can tell. I'll just save this. So wait, I have not taken attendance yet. Wait. I'll take. So total 33 are present. Don't give attendance. So I have this meet attendance. From that, I will take your attendance. No need to type in the chat box. Okay. So I have taken your attendance. So total 33 students are present today. Good. Okay. So with this, today's lecture ends. Thank you very much. You can leave now.